Okay, so how is everyone today? Good, I hope. All right. So, so we did the guess the natural game. That's that assignment is posted. Any questions about that one? So any questions about the guess the natural game? All right. Yes?
So, I actually want us to call upon some other function for the aux section. We have aux0 within it, and then we want us to call it a specific value. Do we call that value f, 0 or f, 1 for this amount?
Okay. I think I understand the question. So I'll answer your question in sort of a little bit indirect. An example is that the human Fibonacci function, a couple lectures ago, we defined it like this. We said that we have two functions, g with signature naturals to naturals, whose purpose is that g of n should be the nth Fibonacci number, and then we have g tilde, whose signature is n cross n to n, to n. Like that. And this pair of functions, this g tilde is called an auxiliary function, and their definitions are like this. So g of n is just g tilde of n, and then I'm going to, whoops. So this actually needs to be, I actually need another one, right? So it's n. 3 n's, and then to n like that. So I'm going to leave those two slots open for just a moment, and then remind you that the definition of g tilde is this. So n, this n right here is just some kind of counter, more or less, and when the counter gets to 0, then we're done. And then A and B, what those are is in the human Fibonacci procedure, you always know two of them, right? And then you use those two to find the next one, and then you forget the least one, and then you use the two you know now to get the next one, etc. So the definition here is going to be that in one case we're going to do something when n is 0, and then we're going to have a different case for every other case. So otherwise, so the recursive case looks like this. We say, well, so the second argument, that screen looks kind of washed out to me. Does that look washed out to you? Do any of those look promising? Brightness? Auto-tune? Yeah, do that. That improved the color a little bit, did it? Okay, so is it visible? Okay. So the second argument is the lesser of the pair that you know, and the third argument is the greater one. So for this lesser and greater pair, the new lesser and greater pair respectively are, so the new small one is the old big one. And what's the new big one? The sum of that pair, right? Like that. And then the first argument, as was initially said, what it is, it's a counter. So we'll subtract 1 from the counter, you know, which basically conceptually means that we performed 1 unit of work. So in the specific case when the counter has become 0, the answer is the lesser of the pair that you currently know, which is to say that if n is 0, then the answer is A. All right. So then now, this is not a complete definition because we haven't filled in those blanks. So what goes in there and why? Since you asked the question. 0 and 1. Okay. Why those? Uh-huh. Right. More or less because that's the first pair of numbers in the Fibonacci sequence. That's the definition. So what effectively what I'm saying to you is what function were we talking about? Oh yeah, the up one. So effectively what I'm saying to you is that you're talking about the up function. The up function is a function, and I'll just, for the purposes of this page, I'll just write u. Now what u is that the argument to u is itself a function. Okay, now that's a little bit disturbing. It's a little bit disturbing because until this point in the class, you've written some MATLAB functions, and we've talked about some functions on the page, but for example, for this g tilde, all of its arguments are numbers, right? That's a number, that's a number, that's a number. But it's perfectly fine for you to for one of the variables, for one of the arguments to itself be a function. So to sort of justify that claim, what I want you to observe is that how about, so this is like an aside now. In calculus class, if your instructor writes this, then what are they asking you to do? They're asking you to calculate a derivative, right? And what kind of thing is x squared? That's a function, right? And so what is the derivative of x squared? It's 2x. So what I'm telling you is that the derivative is a function. Okay? And then what kind of input do you give it? A function. And what kind of output does it produce? A function, right? So the input to a function can be a function. And the output to a function the output of a function can also be a function. So a function whose input is functions and whose outputs are also functions, those are near and dear to mathematicians' hearts, and such things are called operators. All right. Can you think of a function whose input is a function and whose output is a number? Which one?
Evaluation.
That's a good one, right? So then we could make a function that evaluates another function at 0. So we could say like that you know, I could write EV like this. So EV 0, EV 0, and I could say like, okay, what's some function? How about cosine? Cosine's a function, right? So we can evaluate EV of 0 at cosine. Okay, so cosine is a function, and what that's saying is that take that function and evaluate it at 0. Okay, what do you get when you evaluate cosine at 0? You get 1. So evaluation at 0 is a function whose input is a function, whose output is a number. But there's even a more famous, I guess, one, is that I could say, well, what about this? I could say that suppose that we have a function that is usually written like this. Whoops. I'm going to write the function like this. So blah, blah. And then what this is I'm viewing this as a function, and you're supposed to fill in the blank. You know? So like an example would be, well, what if we took the function x squared and jammed it into that thing, right? Then you'd be asking, what's the integral of x squared on the interval 0 to 1? And the answer is some number, right? Whatever it is. So what I want you to observe then is that well, what's the signature for 2x? So 2x has signature what? Viewing it as a function. What kind of input does it accept? Real. And what kind of output does it produce? Real. So it has signature real to real. So 2 times x has signature real to real. So what I'm telling you is that derivative itself has a signature. What kind of input does the derivative accept? Yeah, its input is a function which has signature real to real. That's the kind of thing you're supposed to give it. Right? You give it, for example, x squared. You give it a real to real. And then given that real to real, what kind of thing does it produce? Right. It produces a real to real. So that's the signature of derivative. That kind of input, that kind of output. Okay. So now that you see that we've got signatures within signatures, understand that in principle it can nest as far as you care to take it, right? I could replace, for example, you could imagine I could take that real and replace it with yet another, say, real to real, and that would be something else entirely. So what I'm telling you is that fine. What is the name of when you take derivative and you turn it around, and instead of going that way, you go that way? Yeah, that's antiderivative, right? So which is to say that this thing right here, and taking that as the spot where you're supposed to put the input, taking that, the antiderivative also has signature reals to reals to reals to reals. Because when you anti-differentiate a function, the result is another function. Almost. I have to say almost because this plus, the plus c business, that's a little slippery. But at any rate, that's more or less correct. And then, if we do this, if I change it from antiderivative to integral, like that, then what kind of thing is the input? Right. Real to real. And then what kind of thing is the output? Just a real. So, antiderivative has that signature. Integral has that signature. And they're not close in that sense. They're not they're not similar to each other at all. Okay, it would be like if you had two vending machines, and they're both vending machines, and the vending machine on the left, has like candy and snacks and stuff in it, and the other one has like I can't like cats or something in it. It's not even close, right? That one gives you candy, and the other one gives you cats. They're not. They're both vending machines, sure, but they're not very similar. So for that reason, whenever I teach calculus, I always refer to this one as antiderivative and this one as integral. And I utterly and absolutely refuse to use the names definite and indefinite integral. Okay, I think that's about as clever as saying red colors and non-red colors. It's not very descriptive. Good. So now that being the case, the up function, that's so blown out looking. Can y'all see that? Yeah, okay. So what's the signature of the up function? What kind of thing does it take as input? Well, it takes the oracle function, right? So the input to the up function is the oracle is an oracle function whose signature is you give the oracle function a natural, and it responds to you with one of three responses: -1, 0, or 1. So the input to the up function is a function like that. What kind of thing does it output? What it does is it gives you two naturals, a lower bound and an upper bound for the answer, right? So the output is natural cross natural. So the up function is a function whose input is an oracle function and whose output is a pair of naturals, which represent which represent the lower and upper bounds respectively. And the way that the instructions say to do this is that, in fact, you're supposed to define an auxiliary function in the same kind of way that we made an auxiliary function for the Fibonacci sequence. And so this auxiliary function, the first input is the same as that one, and then we've got these two more inputs, because that's kind of like, you can think of that where we're working. So the auxiliary function, which in the instructions is called up0, will have signature naturals. So the first input is the oracle function. And then the second input is a natural. And then the output is that pair of naturals. So it's that thing in the end. So you asked me a question about 40 minutes ago. You're asking about that, and in the end the question was what is it supposed to be? And then I asked you concerning the Fibonacci things, what's supposed to go here, and you said 0 and 1, and I said why, and you said that's the definition. And so what I'm telling you is that the up function of f is defined as the auxiliary function evaluated at f, where f is some oracle function, and then in the end your question sort of boils down to what goes there, and the answer is whatever the definition is. So you got to read it. You got to read the definition. So. And I promised it's there. So well, I'll start mentioning it and then move on to the new material. In the end, it says that the up function is supposed to do the following: is that remember what the game is that there's an oracle, and the oracle has some natural number that they're thinking of but not telling you, and you can ask the oracle to evaluate at any natural, and it will respond with -1, 0, or 1, which means that you guessed too low, you guessed correctly, or you guessed too high, respectively. And the up function, in the instructions for the up function, it says that you're supposed to guess sequential powers of 2, starting at 1. That's the definition of the up function. Okay? Other questions? Yeah?
So that means the oracle's never going to think 0?
No, it could,
Okay.
because 0 is a natural. But that's one of the things that I purposefully am being a little bit loose about, not trying to tell you, because I want you to come to I want you to come, figure out what am I supposed to do, So if you're supposed to ask the oracle about sequential powers of 2 starting at 1, then you must do that in order for your program to be correct. But what if you ask about 1 and the oracle says that's too high? Then what? You've still got to output 2 naturals. I leave it to you to try and consider it. Other questions? Yes? yes, you need to evaluate f. So you're going to have to say f of, that argument, whatever you name it. You have to treat it just like a function. So you plug in something, and then the oracle and the output of f of whatever is either going to be -1, 0, or 1. So sort of for this assignment, one of the conceptual problems is that this is sort of like for many of you, will be the first time where you are coming face to face with the fact that functions, the input to a function, doesn't have to be a number. It could be a lot of things. It could even be a function, right? So derivative is a function whose input is a function and whose output is a function. Antiderivative is a function whose input is a function and whose output is a function. And integral is a function whose input is a function and whose output is a number. So this signature, functions to functions, such things are called operators. This signature, functions to reals, such things are called functionals. And those things are near and dear to mathematicians' hearts. Yes? No, I haven't fixed it yet. I will, though. Good. Other questions? All right. So now let's get to it. So we were talking about something. Oh yeah, we were talking about division and divisibility and order. So to sort of summarize that, if we're sort of in the context where we say let m and n be in the naturals, then the linear order is so the linear order is the thing that you know as less or equal. So no surprise there. This is a thing that you know. So you could write m less or equal n. Okay, and it means exactly what you already know it to mean. Now, I could write, for example, this. I could write 70 less or equal 23. So now, is that an inequality? Yeah, it is. It's an inequality. And if you're uncomfortable with me saying that it's an inequality, it's because you have two things identified in your head that are actually separate. So this is an inequality. What is its logical value? It's false. So it's an inequality. Its value is false. Okay. So then similarly, I could write, how about this one? 23 less or equal 70. Is that an inequality? Yes. What is its logical value? True. What I want you to see from this, what that means, is that in some sense what that symbol is you can view it as the name of a function. It's a function whose name is less or equal, whose name is that. And then since we're talking about the naturals, it takes two arguments. Now we usually write, we write them on one on the left side and one on the right side, but at any rate it takes two arguments. And so the input is naturals cross naturals. And then what kind of thing does the less or equal function produce? A logical, right? Which is I'll denote as just boldface L. So what I mean to say is that viewing it in that way, we could write something like, well, what if we evaluate less or equal at, say, 20, 18? Now, of course, the usual way to write that is to put the less or equal in between those. Okay, but I'm gonna write it that way. So I'm gonna write it like this. So what is the value? Less or equal evaluated at 20, 18. It's false. And I'm just taking f to mean false. Of course, that means 20 less or equal 18. Okay, then I could swap those, and then it would be, you'd be, writing, how about less or equal evaluated at 18, 20? Then it's true. Okay, but it's a function, and this is called the linear order, or on the naturals. So any question about it? So it's exactly the thing that you know. Now, besides the linear order, I can also say let m and n be in the naturals. The division order is that thing that we were talking about last time. The thing we were talking about last time, and that is the question about whether or not A divides B, whether or not A is a divisor of B. So the division order, which is to say that when you write m, now in your previous, if you've ever seen this before, then the way it's written down is probably just a single vertical bar. But I think that's a particularly bad idea, and I'm campaigning to get all of my mathematician colleagues to agree that we're not going to do that anymore, with small success. But the problem with this is that the way you read this is that you say that m divides b. M divides n. But the problem of it is that so if you look at inequality in the linear order, the way that you teach this to kids, like little kids, is you say, well, you got two numbers there, and that's an alligator, right? And then the alligator wants to eat the bigger number, right? So the mouth is supposed to go that way. That's how you teach it to kids. And the problem with this, is, or if you like, a nice thing about this one, is that you can take this sentence and turn it around like this. You can write 18 and 20, and you can make sure that it's still true by turning the alligator around, right? No, wait. Okay, so it's still false, right? Good. Sorry. Let me just make sure I write down an example that was what I said it was going to be. So this one is true, and then you can turn it around. You can write the 30 right there and the 10 there, and you can arrange it so that it's still true by turning the alligator around. So what I'm saying is that the problem with this notation is that it has a vertical symmetry. So if you reflect it, it looks the same, unlike the alligator. So the way we're going to write it in our class is like that, so that it's not vertically symmetric, horizontally symmetric, and you really can flip it around. Okay, so this means when this is true, that implies that there exists a p. I don't want to use p. How about an a in the naturals, such that this is m is a divisor of n. So now I need an equation. So what is it? So is that we should be able to factor in, and m should be one of the factors. So this should be equal to m multiplied by a. Okay, so then so that means that according to what we wrote, not only is m a divisor of n, but what else is? So is a, right? So they're both divisors. All right. Now, concerning that, I've got a question for you. So if m and n are naturals, then so here's just some facts that I'll list out. So for any natural, and I'll stick with m, there are at least two naturals which divide m. What two naturals definitely divide m? One in itself, right? So this statement, 1 division less than m, like that. 1 is a divisor of m. That's true. And then what else must be true? M is also a divisor of m. And that's true for every natural. All right. So if it is the case that in fact those are the only divisors, then m is special and it's called what? Prime. Okay, so an example of a prime is 11. So 1 and 11 are the only natural divisors of 11. Something that's not prime is 12, because 2 is a divisor of 12, 3, 4, lots of them. So there's an interesting phrase. Well, let me say it like this. Concerning the set of all prime numbers, which one is least? 2 is, right? So it's 2 because part of the definition of a prime number, you might sort of say that, well, what are the divisors of 1? 1 in itself. So that you might kind of be led to believe that, well, okay, maybe we can consider 1 to be a prime, but there's good reasons to say that no, not really. We don't want 1 to be a prime. So a prime number has to be a number where these are the only divisors, and moreover, it has to be more than 1. So the least divisor is, the least prime is 2. So someone else, respond please. What 2 is the least prime. What do you suppose is meant by an odd prime? So if I were to write the sentence, let P be an odd prime. What does that mean? Yeah, any prime except 2. Right, because if you were to list the primes out, they'd be 2, 3, 5, blah, blah, blah. So if you list them all out and you say, if you're writing a math thing and you say, let P be an odd prime, you're just saying that suppose we have any prime number except 2. Because 2 is the only even prime, which is the subject of the joke that 2 is not an odd prime. It's the oddest prime. Because as it happens, 2 shows up like everywhere, right? Because of symmetry and things like that, so 2 is everywhere. Fine. So we have this. Now, concerning this, the linear order, that says less or equal. And then, of course, you also know this other thing, less than. Okay? So then, if we were to take the same number twice, like 20 and 20, is 20 less or equal 20? Yeah. How about is 20 less than 20? No. So my question to you is that is the division order, is it like less than or equal, or is it like less than in that sense? It's like less or equal in that sense, right? Because this is saying that m is division less than m. Right? So this is true in the same kind of way that 20 is less or equal 20. All right. Now, the justification for these two statements is, after all, that we should be able to write an equation like that. So we should be able to write that m is equal to what? For these two. 1 times m, right? So as a result, 1 is a divisor of m, and so is m. Okay. Now, 1 divides everything. 1 divides everything, so here's something that's a little bit disturbing. How about, is this statement true? M is a divisor of 0, so, and in fact I'm saying even for all m. If it's true, then we should be able to write an equation. Okay, we should be able to factorize 0, and m should be one of the factors. So we should be able to write 0 is equal to m multiplied by 0. So m is a divisor of 0. All right. Well, if that's true, or even if we hadn't written that down, then that's got to be true, and in fact that's got to be true apparently for all naturals. So what about this one? Is that true? Yeah, it's true because of that one, right? I should be able to replace those m's with zeros. It's got to be true for that one because I should be able to replace that one m with a 0. And just to make sure that we're all okay with this, how can we write an equation that says 0 is equal to some factorization of 0 that has 0 in it? Okay. So does 0 factor that way? It sure does. All right. Fine. So any questions so far? All right. Now, taking those things, the painful bit here is this. Suppose that I ask about the minimum of the naturals. And now I need to be specific. What I mean is the minimum where order is reckoned using less or equal. So what is the least natural in the less or equal order? It's 0. Okay, and then what is the correct response if I ask for the maximum of the naturals in the less or equal order? There is none. All right. What if I ask for the minimum of the naturals, but I'm not talking about the linear order, if I'm talking about the division order? What is the minimum when order is given by division order? It's 1, right? The question is that what number can always be written on the left side of this? And the answer is 1. 1. Because 1 divides everything. Does 0 divide everything? No, because, for example, if you wanted to factor 10, can you write 10 is equal to 0 multiplied by something? No, so 0 is not a factor of 10. So, in fact, the minimum, the least natural is 1. But you have to understand that that's least in the division order sense. Similarly, how about the maximum natural in the division order sense? What's the greatest natural? It's 0. Because you're asking, is there a natural that you can write one of these inequalities here with the division order, and 0 can always be on the right? Sorry, and this thing, is it the case that 0 can always be on the right? And the answer is yeah, because of these equations. So what I want you to see is that we've got 2 different orders on the naturals. This thing that you knew from grade school, which now we're going to call the linear order, and this other thing that we're talking about called the division order. And it's a little bit disturbing that they don't have the same minimum. Right? The minimum of the linear order is 0. The minimum of the division order is 1. And then concerning the maximums, the linear order doesn't have any maximum, but the division order does have a maximum, so that's already surprising. And furthermore, the maximum is 0, which is the minimum in the other order. That's a little disturbing, but it's a fact. Yes?
So why do you call the division order?
I'm sorry?
Why do you call the division order ordering? It's not ordering.
Well, it's an order, but what it is that it doesn't have this property. It doesn't have it's not the same kind of thing as this, and so they're both called orders, but this kind is special in that it's going to be called a total linear order. Okay, so then now the totality of it will be this kind of statement. Suppose that we take 2 numbers, 23 and 70. We've got 2 numbers. So then we could do 23 less or equal 70. And then I'll say or, and I'll rewrite that again, but I'll flip these. Okay, so now this evaluation, false or true? True. And this one, false. So the totality of it is that you should be able to take any two naturals, and either that one or the other one has to be true. Either this one or that one. In fact, it could be both, and in that case, that would mean that those two numbers are the same number. So one of these must be true. At least one must be true. But, well, how about concerning the division order? 23 is a divisor of 70. False or true? False. Switching them around, 70 is a divisor of 23. False or true? False. So notice that, in fact, both of them are false. That's much different than less or equal, where at least one of them must be true. All right. Now, one thing I do want to you to notice is that even though less or equal, the linear order, and division order, they're not the same, they do have some connections because, for example, we can say that if we say let n and m be natural, then we can say the following. So I'm going to write something that's almost correct, but not quite correct, and I want you to fix it. So if this is true, n is a divisor of m. If that's true, that implies n less or equal m. So this is almost true, but we need to modify it just a little bit to make sure it's right. So what's not right about this? So what I mean is that, you know, for example, is this true to a divisor of 10? That's true. How about 2 less or equal 10? Is that true? Yes. So what I'm saying is that if that one is true, then that one is true. But in fact, it's not true for every n and m. Yeah, we can't have this one being 0, right? Because is 2 a divisor of 0? Yeah, everything divides 0. Is 2 less than 0? It isn't. So this is this works. It works, in fact, for all m greater than 0. All right. So they're different, but not entirely different. Now, it's called the linear order because of the following. Linear order. So if I consider the set that just contains, say, 4, 5, 6. Then what I'm going to do is I'm going to write the following. I'm going to say that when I draw an arc, an arrow from m to n, like that, with tail at m and head at n, that is going to mean that m is less or equal to n. So what I'm saying is that that's this thing that we write, but now I want to start drawing a picture, and the way I'm going to do it is that I'm going to draw arcs when that's true. So 4 to 5, that goes there because, yes, 4 is less or equal 5. 5 to there is that. So 4 is less or equal to 5. Is there anything else 4 is less or equal to? 6. So I'm going to draw that arc. Is there anything else that 4 is less or equal to? Which one? Just concerning these. Itself, right? Okay, and then 5, is there anything else it's less or equal to? Itself, right? And then 6, itself. So now these self loops, that's the statement that 5 is less or equal 5, 6 is less or equal 6, etc. Now when you're talking about these things, there's a name, there's an adjective, an R word that I'm fishing for, that these self loops are. So what are they? That's reflexivity, right? Which is to say that the statement m less or equal to m, that's called reflexivity. Reflexive. And now, to some extent, I kind of hope that you rebel just a little bit with me drawing that arc from 4 to 6. Because after all, because if 4 is less than 5 and 5 is less than 6, then surely 4 is less than 6, right? So that's a consequence. So what's the name for that consequence? Yeah, it's transitivity, right? So it's saying that A less or equal B and B less or equal C implies A less or equal C. This is called transitivity. Transitive. Now, if it were the case, if in addition to that you have this property, that either that one or that one is true, which is true for the linear order, that's called totality. But I'm going to ignore that for now. So now what I want to do is I want to simplify this picture. I want to simplify the picture by deleting everything that is a consequence of reflexivity and everything that's a consequence of transitivity. So in this picture, what are the consequences of reflexivity? The self loops, right? So I'm not going to draw that. It just complicates the picture. And furthermore, what are the consequences of what can be understood to be a consequence of transitivity? The arc from 4 to 6, right? So supposing that we delete all of that information and just understand it to be present, then that means that you can draw this picture like this. No self loops, no transitive arcs. There's a name for this kind of thing. Taking this picture to that picture, just for the curious, this is called a transitive reduction of this. And notice that you can draw it in a line. That's why it's called the linear order. So 4, 5, 6, there's nothing special about them. I could have selected all the naturals and delete all the reflexive loops and all the transitive arcs, and then it would just be straight line, which is why this is called the linear order. Now concerning the division order. To begin with, if we have something simple, if I consider the set that is p squared, p cubed, and where p is a prime, yeah, prime will be fine. It doesn't have to be prime, it's just any number, any natural more than 1, really. P prime. And if I write that that means, in this case, that m is a divisor of n. So just like that, then I can write these p squared, p cubed. So then I'm not going to bother writing the reflexive or transitive arcs. So of course p is a divisor of p, and p squared a divisor of p squared, etc. Is p a divisor of p squared? It is, so I'll draw that arc. Is p squared a divisor of p cubed? It is. So I'll ignore the self loops, the reflexive loops, and p is a divisor of p cubed. So I could draw an arc, but I'm not going to draw it because that's a consequence there. So now, the division order in that kind of, for this particular set, can be drawn in a line. That's interesting. So it is in that way sort of like this. But now suppose that that we have a more interesting set that's not just powers of a prime. What if instead we have two primes? I could say let P and Q be prime, and furthermore, they're not the same prime. So if you want to have something concrete in your mind, you could just take the first two primes, 2 and 3. Now, what I'm going to do is that I want to consider the sequence 1, P squared, P cubed. And I want you to interpret that as meaning in that first column I have 0 P's, so there's none of them, and then 1, and then 2, and then 3 P's. And similarly, 1 for that one. And then I'm going to write Q and Q squared. And what I want you to observe here is that now I'm going to write the product of all of these. But in fact, I'm not interested in just one, so I don't want that one. But I do want P times 1, so that'd be P. I do want P squared times 1, so that'd be P squared, P cubed, like that. I do want these, so this would be Q and Q squared, like that. And then what do I write there? PQ, right? So PQ, P squared Q, P cubed Q, and then here PQ squared, PQ cubed, no, P squared Q squared, that's what I want, and then P cubed Q squared. So there are 11 entries there, because it would be 12, but I said I didn't want one, so I left that one out. So now I want to consider the set here, this set. Now how are they ordered in the division order? So you could linearly order them. They'd fall somewhere on the line, and you could linearly order them. But I'm not talking about that. I'm talking about the division order. So if I write, if I do P squared, and P cubed, then we already talked about that on the previous page. It would look like that, ignoring the transitive and reflexive arcs. So that's 3 of them, right? That's those 3. And suppose that I want to get the 3 immediately below them. Well, the way that you get the ones below them is that you just multiply everything by q. So if right here I put PQ, okay, then well, is P a divisor of PQ? It is. So there's an arc that goes there. And for this one, this would be P squared Q. And down here, this would be P cubed Q. So then now P squared is that and is that. Good. But now also going to the right, I also have arcs. Because is PQ a divisor of P squared Q? It is. Okay, what about diagonally, like right here? Is P a divisor of P squared Q? It is, right? So what I'm asking, is this one a divisor of that one? It is. But I'm not going to draw that arc. Why not? It's transitive, right? The question is can I get from that point to that point following the arrows that currently exist? I can, right? So I don't need to draw a diagonal arc. All right. You can probably imagine what's coming next. So this will be what? PQ squared. What am I doing here? Thank you. P squared, Q squared. And then P cubed, Q squared. Okay, again. Whoops. So like that. So right now I have 9. Which ones are missing? Q and Q squared. If I want to make a nice looking drawing, where does Q go? Yeah, it goes right there. So that'd be Q there. So Q would go like that. And then Q squared, well, that'd be here. Oops, that's not close to that. All right, so that's all 11 of them. Interesting. And here's the deal: try as you might, you can't rearrange these or delete some arcs using transitive cleverness or anything like that to ever get these to be in a line. They will never be in a linear order. This is the lattice. That's why the other one is called the linear order, and this one is not called a linear order. Also, concerning, for example, say like p squared, that point right there, and pq squared. So can you get from this point to that point following the arrows? You cannot. You could if you were allowed to follow the arrows the wrong way, but that's not allowed. So you can't get from here to here. That means that p squared is not a divisor of pq squared. That's what that means. It's not a divisor. So how about, can you make it from this one to that one following the arrows? You can't. So the thing is that the linear order, because everything's in a line, when you plot them on the thing, you're either going to be able to go from here to there or the other way, because they're all in a line. But you can't do it here. Now, one thing that's a little bit disturbing, to make sure the whole point is clear, is that now in the division order, what's the least natural? 1. So that means that all such division lattices, they all have a 1 here. An implied 1. You usually don't write it. And then what's the greatest natural? 0. So notice that from any point on the lattice, you can always make it to 0. And if you only traverse in the backwards direction, you can always make it to 1. Okay. Any question about it? Now, we've got a couple things to talk about, but we're not doing it today. We're going to do it next time. I want to foreshadow something. Is that next lecture we're going to talk about this thing that you learned in Miss Harris's class, the greatest common divisor. Right? So like, for example, the greatest common divisor of, I don't know, like 24 and 32 is 8, right? It's 8. But here's the deal. You've got this word here, greatest, which sort of naturally to us means, like the biggest one. But this greatest is actually not referring to the linear order. What's it referring to? It's referring to the division order. It's referring to the division order. So what that means, for example, I could ask, again, I'm just foreshadowing what's going to happen next time. If we have a function called GCD that is the greatest common divisor, and then I take some number, like 2370, and then I ask, what's the greatest common divisor of 2370 and 0? Well, what is it? So, what is the greatest divisor of 2370? 2370. Okay, both in the linear order and in the division order, for that matter. What is the greatest divisor of 0? Or, alternatively, what is the set of all the divisors of 0? All the naturals. All of them. So what's the greatest common divisor of 23 and 0? 2370. Now, all right. I find my experience tells me that some of you can say, all right. But now I'm going to ask, what is the greatest common divisor of 0 and 0? That's not true. That's not true. So let me ask, how about 1,000? Does 1,000 divide 0? Yeah, because 0 is 1,000 times 0. So can 0 be factored, and 1,000 is one of the factors? Yeah. Does 1,000,000 divide 0? Yeah. How about 1,000,000,000? Yes, of course it does. What's the greatest common divisor of 0 and 0? 0. To which you might say, but wait a second, you just told me that 1,000 is a divisor of 0, and clearly 1,000 is more than 0. To which I say, I'm not talking about the linear order. I'm talking about the division order. What is the maximum of the naturals according to the division order? 0. Okay, so we'll talk more about that. I've still got a couple things to say. We'll talk more about that next time, but I just want to get your brain working on that so that you can come to terms with that. Good. So now, concerning this, we can ask a question. So like, here's a grade school question. Divide divide 172 by 8. Okay, and I'm not talking about type that into your calculator and give me a decimal. I'm not talking about that. Rather, I'm talking about this thing, where Miss Harris says, okay, 172 is in the house, and 8 is outside the house, and 8 wants to come in. And then you ask, how many times can 8 go into 1? Oh, it can't. So then you take another digit and say, okay, how many times can 8 go into 17? Twice. Of course, understand that that's not really a 2. That's actually a 20, right? Because that's in the tens position. The 2 jumps off the house because it's doing a division problem. And then hits the 8 on the way down. And then you write 16. Of course, understand that's not really a 16. That's 160. Because that's not a 2. That's a 20. But you ignore that for a moment and you write 1 there, and then you carry down the 2. And the reason why you carry down the 2 is because that's really 160. All right, then 8 doesn't go into 1, and that's good, because if it did, we would have made an error. And 8 goes into 12 once, so that 1 jumps off the house, hits the 8 on the way down, you write it right there, and you subtract, and you get a 4. So the consequence of this is that we have made the following conclusion, is that the quotient is 21, and the remainder is 4, which means that if you were to break 172 M&Ms into groups of size 8, you'd be able to make 21 such groups, and there would be 4 left over. Combining all of these, they can be written in the following sentence, that 172 is 8 multiplied by 21 plus 4. But what I want you to view this as, this question, is that it is like a function, a procedure, where your teacher gives you 2 inputs, and you produce 2 outputs. So you're given these 2, you produce those 2, and then they're all related to each other according to that. So this thing that you learned in grade school is that is called Euclidean division. Okay, so we're just going to write down the definition of it, since I think that's probably all the time we have to do. Okay, and it is the following, is that I could say let n and d be in the naturals, and I want d to be greater than 0, meaning anything that's not 0. Then there exists, which is the meaning of that symbol, and moreover there exists just 1. So the meaning of the exclamation mark is there exists unique. So there are some things, and in fact just 1. Q and R in the naturals such that N is equal to D multiplied by Q plus R, and 0 is less or equal, R is less than D. So strictly speaking, I don't have to write the 0 less or equal, because after all, I did say that R is a natural. So of course that's true. But what this means is that, if you were in grade school and you were asked to take M&Ms and break them into groups of size 4, and the teacher said, and if you do it right, you get to eat them, And if there were 22 M&Ms and you want to make groups of size 4, would you say, I was able to make 4 groups and that's it? Would that be what you'd say? What if you made 4 groups of size 4? How many M&Ms would that be? That'd be 16. Would there be enough to make another group? Yeah, because there'd be 6 more. Could you make another group? Yeah, you would. You could, and you would, because this is M&Ms and you're a child and this is serious business. Right? So then what this means is that you've made all possible groups. It's not possible to make even one more group because the size of the group is D. So last thing, and then we're done. So this is called the quotient, just like up there. This is called the remainder. Unfortunately, these two things have very similar sounding names. This one is called the dividend. Dividend. This one is called the divisor. The meaning of those suffixes is this is the one it's happening to, so this is the object in the sentence, and the meaning of OR means that is the subject in the sentence. So this is the thing being divided, and that is the thing doing the dividing. And then taking those all together, the quotient, conceptually what it is, that's the number of groups you're able to make. And then the remainder is what is left over when you can't make any more groups. All right, so have a nice Thursday.